want to give an introduction to Bayesian methods for analyzing data. It's going to be more focused on just the idea of doing Bayesian statistics, what lies behind it, and what's different about it. So, to begin, I would just review our concept of probability. What is it? First and foremost, it was invented as a way of quantifying uncertainty. And, a lot of the technology that we use today had fairly base motives at its inception. In this case, it was better to better, make money during games of chance, gambling. But the definition of probability that we use and that we teach, that we learn as undergraduates is this one, which I've defined before. It's a long-run proportion. The proportion of times that the event would occur if we repeated a random trial over and over again under the same conditions. And then a probability distribution is a list of all of the possible outcomes of a random trial and their probabilities of occurrence, their long-run fractions of occurring. And then, with this definition, there are all kinds of statements like those that we make when we analyze data, but also in everyday life. If we toss a fair coin, what's the probability of 10 heads in a row? We can calculate that if it's a fair coin. Or more statistical, if we assign treatments randomly to subject, what's the probability that the sample mean difference between treatments will be greater than one standard deviation? That's the kind of calculation you would do if you're calculating power. There are also processes in biology that are stochastic, like genetic drift. Under a process of genetic drift, what's the probability of fixation of a rare allele? And then the mighty p-value. What's the probability of a result at least as extreme as that observed if the null hypothesis is true? In all cases, we have a probability model that underlies these that allows us to calculate the probabilities, and sampling error is the source of uncertainty in every case. But there are also probability statements that we can make or that we might run into that don't make sense under the definition of probability that we gave. What's the probability that Iran is building nuclear weapons? Well, it's not like there's a series of random trials, all of them called Iran, and some fraction of them they're building nuclear weapons, and in others they are not. So what does it mean to say that Iran, what's the probability? Closer to biology, what's the probability that the hippos are the sister group to the whales? Even closer to home, what's the probability that the fish sampled from this newly discovered lake represents two species rather than just one? What's the probability that polar bears will be extinct in the wild in 40 years? So these are statements about things that we're uncertain about. And then the question is, can we answer them? Can we put the answer on a 0 to 1 scale in the same way that we can put long-run frequency? They don't make sense in our concept of probability, the one that we use, because either Iran is building nuclear weapons or not. There are no random trials here. What's the probability the hippos are the sister group to the whales? Well, either they are or they're not. There's no random trial here. What's the probability the fish sampled represent two species instead of one? Well, again, no random trial here. Either there's one species or two. It's up to us to figure it out. What's the probability that polar bears will be extinct in the wild in 40 years? Well, there's only one polar bear, so it's difficult to maybe cast this in concept in terms of random trials. But there are stochastic processes like genetic drift where we can calculate probabilities, and so maybe it might be possible to look at the future of polar bears in terms of stochastic processes that lie ahead and actually calculate a probability that makes sense, but I don't know. But there's a big difference between all these cases and the cases I presented before, and that is there is no random trial, there's no sampling error. The source of uncertainty in this case is lack of information, not sampling error. And yet people want to be able to put a number to measure the uncertainty of exactly these kinds of questions. And to do this required an alternative definition of probability. And it's the Bayesian definition of probability. Probability is defined as a measure of a degree of belief associated with the occurrence of an event. That's the Bayesian definition of probability. We're no longer dealing with random trials repeated over and over again. What's a probability distribution in that case? Well, it's all the possible mutually exclusive events that might occur and the degree of belief associated with them. So Bayesian statistics applies all the mathematics of probability, which were developed based on the metric or the definition of probability as a long-run frequency. All the mathematical machinery works for this alternate definition of probability. And Bayesian statistics is basically the development of all these methods to calculate that measure of uncertainty, where uncertainty is now defined not as a long-run frequency, but as a subjective degree of belief. You okay with that? Shall I go on? Bayesian methods are increasingly used in ecology and evolution. We see them more and more. They're not going away. Every year it seems like more and more examples are found. This is a bit of an old school attitude then. Ecologists should be aware that Bayesian methods constitute a radically different way of doing science. Maybe that's a good thing, I don't know. It's not, Bayesian statistics not just another tool to be added into the ecologist's repertoire of statistical methods. Instead, Bayesians categorically reject various tenets of statistics and the scientific method that are currently widely accepted in ecology and other sciences, like the definition of probability itself. Sounds alarming, sounds disastrous, sounds like, whoa, we ought to avoid it, but the fact is we don't. And Mark Mangle, who's written on quantitative ecology, once told me, ecologists are facultative Bayesians. And it's true. You'll read about papers in ecology, in one paragraph will carry out some method that applies a Bayesian definition of probability, and in the next paragraph there'll be a p-value which adopts a completely different definition of probability. And there'll be no shame associated with this whatsoever, even though the word probability is not actually referring to the same thing in those two paragraphs. Well, it is. It's referring to a metric of uncertainty, but the actual definition is completely different in these two cases. My colleague Mike Whitlock has no real issue with Bayesian statistics other than the fact that they should have called it something else besides probability. Brobability. Then we can be really clear when we use the two terms and not pretend that they're the same thing. So it's called Bayesian statistics. The original idea came from the Reverend Bayes. And I want to show you a little bit about where the idea comes from. It comes from applying Bayes' theorem, which by itself is totally harmless. And I'll show you. So the triple test is still used in hospitals and by physicians as a preliminary test of the possibility of Down syndrome in a fetus. It occurs at a rate, Down syndrome occurs at a rate of about 1 in 1,000 pregnancies. And the triple test is not incredibly accurate, but it is cheap. And so it might be used as a first test, and depending on the outcome, then more expensive tests might be used subsequently. It's not very invasive. It carries a very small risk of miscarriage, which is why it's used. And the way to think about how Bayes' theorem works is to think of a probability tree, such as shown here. That there are two events. And one of them is, in this case, whether or not the fetus has Down syndrome. And then the other is the result of the test. And the probabilities listed here are conditional probabilities. What we're going to list is the probability that a test result is positive given that a fetus has Down syndrome. We'll also calculate it given that the fetus does not have Down syndrome. So we learned about conditional probabilities and likelihood is the first step in the development of analyses using Bayes' theorem. So conditional probability is the probability of that event occurring given that some condition is met. And it turns out, approximately, the probability of a positive test result from the triple test is 0.6, so it's not highly diagnostic, given that a fetus has Down syndrome. So 1 in 1,000, 999 of 1,000, yes and no. Okay, so Down syndrome is reasonably rare. If a fetus has Down syndrome, then the probability is 0.6 of a positive result. A positive test result and 40% not. If the fetus does not have Down syndrome, there's only a 5% chance that the fetus will test positive, and a 95% chance that the fetus will not test positive. And since these are all mutually exclusive paths, the probabilities of each of them will sum to 1. And one can calculate this probability simply by multiplying the two all the way down. Okay, so that's how a probability tree works. It's a very convenient accounting method. So what's the probability of a positive test result given that the fetus has Down syndrome? So those are the things we know. But what we really want to know is what's the probability that the fetus has Down syndrome given that the test is positive? So we want to invert the probability. And we can use the probability tree to give us the answer to this. What are the two paths from the origin to the end, to the tip of this probability tree that have a positive test result as the outcome? And the answer is this and this. So if we had 10,000 infants, 6 of them would both test positive and have Down syndrome, whereas 4,995 will test positive but not have Down syndrome. And so what's the probability of Down syndrome given the test result is positive is 0.006 over the sum of those two things, which is 0.012. In other words, 1.2%, which is counterintuitive. Even though 60% of the yeses are detected positive, and only 5% are the no's result in a positive test. Down syndrome is rare, and the vast majority of positive test results come from infants that do not have Down syndrome. And this calculation is formalized in Bayes' theorem. The probability of A given B, when we know the probability of B given A and the probability of A to begin with. So there's B given A, not B given A. B given not A, not B given not A. And so the numerator is, we just want to know the probability of Down syndrome given a test positive, and we would calculate it in this way. All of the possibilities are on the denominator, and the main probability of interest is in the numerator. So the calculation in the previous slide was basically exactly that. So what is maybe more controversial, or at least was controversial in the past, is how Bayes' theorem is used. So forensic evidence. Bayesian inference can be used in a court of law to quantify evidence for and against the guilt of a defendant based on a match to DNA evidence left at the crime scene. So, the various situations in which DNA tests are used, say to establish paternity. She says he's the father, he says I'm not the father. So tests can be conducted, and we can carry out these tests, and we can construct a probability tree where the two possible things that we want to distinguish between are the defendant is guilty or he's not guilty. He's the father, he's not the father. What's the probability of a DNA match if the defendant is guilty? Well, let's imagine that the test is pretty good. There's no errors, it doesn't get sent to the wrong lab, there are no chemical mix-ups. But the probability is 1 that if he's guilty, there's a DNA match. But also important is the possibility of a DNA match if the defendant is not guilty, didn't actually leave blood at the scene. Let's just, for the purposes of this example, say it's actually 1 in a million. It's a pretty small probability of a match if the individual is not guilty. And so the other is 1 minus 1 in a million. So these are all large probabilities and small probabilities. So we can calculate the probability of a match given that he's guilty, or a match given that he's not guilty. But what we really want to know is what's the probability that he's guilty if we see a DNA match. So that's the inverse of the probability, and that's when Bayes' theorem can be used. But in applying this, we also have to know these things. And that is the probability that he's guilty in the first place. What's that? So, application of Bayes' theorem. What's the probability of guilt given a match? It's just this. It's pretty much the same calculation that I showed you for Down syndrome. Just the sum of this number over the sum of this and this. Basically all the outcomes that led to a positive match. In Bayesian statistics, this is called the prior probability. So you've probably heard of prior. The prior. Key to application of Bayesian statistics is the notion that there's a prior probability. And what Bayes' theorem is used for is to calculate the posterior probability. And on the basis of the posterior probability, you'll make your decision. So what we need in order to apply this framework is a prior probability of guilt. Even before we took a DNA sample, we have to come up with a probability that this individual is guilty. Well, let's consider a couple of possibilities for what this prior probability might be, and then what the posterior probability would be calculated as in each case. Let's say this guy lives in a city of 1 million guys, and he's pulled over for some traffic violation, and they somehow get permission to take a blood test, and it turns out to be a match to the blood at a crime scene. Suddenly this guy's in deep trouble. Well, in that case, if he's just some random guy chosen off the street, the prior probability that he's guilty is 1 in a million. And so if we plug that prior probability into the statement, the probability he's actually guilty of the crime is only 50%. He goes free. This is not a very large probability. But if the probability that he's guilty or not guilty is 0.5, if it's just a toss-up at the outset, then he's guilty. And so then the question is, how do we come up with these prior probabilities? And one of the arguments, one of the worrisome things that people have brought to our attention regarding application of Bayesian methods like this is that the prior probability is subjective. How do you decide what prior probability should be? In most cases of paternity, I think, she says he's the father, he says I'm not the father. Okay, let's just say they're right. Each of them is right with the same probability. So we will adopt p equals 0.5 as our prior. So that would represent the state of no information. But it kind of depends on where this guy came from. He was not some random guy pulled over to the side of the road. And she says, he's the father. There's already some reason to believe that he might be the father, like he lives there. But it's for this reason that, to convict somebody, you also have to have some other evidence that puts them maybe in the vicinity, so that the prior probability is not 1 in a million. But that a much larger number could potentially be used. But I sort of picked a couple of extremes just to show you how important the prior probability is in calculating the posterior probability. And this is a case in which it might actually really matter. So Bayesian inference can then be used with data. And one simple way is through hypothesis testing. So in the workshop last week we had a couple of hypotheses about the slope predicted by theory. It's 3/4, or the exponent of a power function. It's 3/4, it's 2/3. And we can represent these as hypothesis 1 and hypothesis 2. And then we can look at the data that we obtained, and we can ask what's the probability of obtaining that data if this hypothesis is true? What's the probability of obtaining the data if that alternate hypothesis is instead true? And that will allow us, if we could come up with these, that will allow us to calculate a posterior probability of this hypothesis. It's the probability that the exponent is 3/4. What's the probability that the exponent is 2/3? Remember, when I say this in the Bayesian context, it's not like there's a series of random trials and in some fraction of them 2/3 is the slope and the other is 3/4. What I'm saying is the strength of my belief that the slope is 3/4 can be calculated using Bayes' theorem. So what we want is the posterior probability. What's the probability H1 given the data? And we can calculate all these things. Probability of getting the data if H1 is true. But as usual, we need a prior probability. What's the prior probability that the slope is 3/4? What's the prior probability that the slope is 2/3? 50-50? The state of no information? I don't know. I mean, the only way in which this could be useful in data analysis if somehow we could all agree what the prior probabilities are. And remember, this is just subjective degree of belief. And if we just don't know, then 0.5 and 0.5 is reasonable for prior probability. Oh, and I also want to point out that this term here, the probability of data given H1, the probability of data given H2, that's the likelihood. If you'll recall. That's the likelihood of H1, and the likelihood of H2 is calculated here. So Bayesian inference is just a little step further from likelihood, which we've already learned about. And is completely conventional in the world of frequentist statistics. But if we can come up with a prior, then we can do more than just calculate a likelihood. We can calculate the probability that the hypothesis is true. Just to summarize then, how Bayesian inference is different from what we usually do. It's not a long one. Probability is not a long run frequency anymore. It's a degree of belief. And we have two probabilities, the prior and the posterior. The prior is the investigator's strength of belief about the hypothesis before the data are gathered. And the posterior probability represents how the uncertainty has changed as a consequence of collecting data. Mathematically, the machinery is the same as that which we use to in frequentist statistics. Mathematically, the value of the hypothesis or parameter is treated as though it has a probability distribution, as though it is a random variable. How does it work in practice? So I'm going to give really simple examples, and this is one that is kind of simplified, but actually one that biologists use all the time. So let's say we go to a lake and we throw in some traps, And we remove the fish and we bring them back to my lab and say, looks like there might be 2 species here. This actually happened. And so then the question is, are there 2 species here? Well, one way we might address this is just looking at their morphological traits. And I'm just going to use one here, gill-raker number, which is a trait that differentiates stickleback species in other lakes where 2 species are found. And here's the frequency distribution of gill-raker number. And so then the question is, well, is this 2 species or is this 1 species? Well, what I want to know is what's the probability that there's 2 species in the lake rather than 1. So to actually calculate these probabilities, we have to start making assumptions. And the assumption that I'm going to make is that we all know when there's only 1 species in a lake that the frequency distribution of gill-raker numbers follows approximately a normal distribution. So what we're going to do is we're going to fit a normal distribution to this measurement on the assumption that there's just 1 species present. And then we can calculate the likelihood of there being just 1 species given the data using the mathematics of the equation for the normal distribution. And then the second hypothesis, there's 2 species in this lake. Each of them has a normal distribution, and so we can calculate using the same mathematics the likelihood of 2 species given the data. And then we can convert this to a posterior probability. What's the probability that there are 2 species in this lake? Well, you might think, well, either there's 1 species or there's 2 species. Probability has nothing to do with it. And true, but under this approach, what we would like more. We'd like to have a number that somehow represents our uncertainty regarding whether 2 species are present or not. So we're going to use Bayes' theorem. We're just going to plug the likelihoods in. And then we're going to calculate a posterior probability, and we're going to first need, however, a prior. What's the prior? Well, here's the, I don't know, maybe 0.5 is reasonable. I don't know if there's 1 species in this lake. I don't know if there's 2 species. So that means a completely uninformed prior. 0.5. But we can also perhaps justify smaller numbers, like most lakes we already know have just 1 species. So the chances of there being 2 a priori might actually be relatively small. 5 in 1,000. And in that case, the evidence is weaker that there's 2 species in the lake, particularly if they're very rare in nature. There's 2 species in the lake. And I don't know if any of you have ever used the program structure. So you calculate or you obtain some genotypes at a series of markers across the genome, and then you throw it into a program called structure or fast structure. Has anyone ever used that in this class? Okay, you'll run into it. TA is nodding here. So this is what structure does, basically. It calculates probabilities like this. What's the probability that there's 1 species using genotype data, and much more genotype data than my simple example, but the principle is exactly the same as I've shown. So that's hypothesis testing in a Bayesian framework. Bayesian statistics can also be used for estimation, and I thought I would just make up an example to again illustrate how this works. So instead of having a specific hypothesis or 2 hypotheses that we'd like to compare, what we're trying to do is ask what's the proportion of males in this newly discovered bee species, or this newly studied bee species. So we just want to calculate a proportion. We already know how to do this in a frequentist context. That's the number of males over the total number of individuals. But we'd like a confidence interval for that. And anyway, that's not the Bayesian calculation of the proportion. To do this, again, well, we know that the proportion of males is somewhere between 0 and 1. And we're going to collect some data, but before we collect the data, we have to come up with a prior probability distribution. So no longer just saying what's the prior probability of these two hypotheses. We now have to have a prior density. We need a probability density function for all the possible proportions that we might obtain. And the non-informative prior, I don't know, who knows? I have no information, is the flat prior, is sometimes called for obvious reasons, and it's the expression total ignorance. I do not know what the proportion is a priori. So I'm going to label this case 1 because I'm going to contrast it with a couple of other cases. And the idea, one of the ideas, in fact one of the arguments in favor of using Bayesian statistics is that you can actually incorporate prior information. And if you have prior information, that can be used to construct a more realistic prior, which will then change the calculation of the posterior. So we know that most species have a sex ratio close to 50-50. And so a more realistic prior would maybe look like something like this. It's highly unusual that they're all males, or that there are no males. So we can give that a low prior probability. And the closer to 0.5, the more likely it is. But we're not saying it's certainly there. It could still be in between, but this is just our prior. We're going to collect data to calculate a posterior distribution. So we can do this. And I'm calling that case 2. But case 3, well again, this uses prior information. These are Hymenoptera. And sex ratios are often female biased in winged reproductive individuals that come from Hymenopteran colonies. And so a perfectly reasonable prior probability would be to have some kind of a beta distribution that looks like this. So again, this scenario represents us using prior information to help us analyze new data in a Bayesian framework. So we can apply Bayes' theorem. We can combine the information in the prior, which is flat in the first case, biased in the third case, and sort of symmetric in the second. And combine that with the likelihood, which is the blue curve here, to calculate a posterior probability. And the blue curve is right underneath the red curve in this case. The likelihood and the posterior probability distribution have exactly the same shape. And that's typically the case when you use an uninformative prior. Like the posterior probability distribution looks a lot like a likelihood. Whereas in these other cases, you can kind of see how the posterior distribution, the red one, is a function of not just the data, the likelihood, but also the prior. Sort of a little bit closer to the prior than to the data. The more information, or the more distinctive the prior is from the likelihood. And so these are the estimates of the proportion of males that we would get in each of those cases. They're a little bit different. They're not amazingly different in this case. But that's mainly because we're actually pretty close to 0.5. So just to recap, what have we done and how is this different from what we normally do? What we do in this case is we have a posterior probability distribution, rather than just posterior or a posterior probability for each of, say, 2 hypotheses. But as I've shown, it depends on the prior, and that again is a potential source of controversy. An advantage of having or using a prior probability distribution is that you can incorporate what's already known. But it's also potentially controversial because it's subjective. What do we already know? To resolve this, we may all come to an agreement that we're just going to use uninformative priors. And that's actually pretty much the standard in analysis of biological data using Bayesian methods. But we could potentially, if we were a team and we all agreed, came up with a consensus of using maybe the frequency distribution of sex ratios to form a prior. And that's not objective because it's actually harvested from a meta-analysis of the literature. Another saving grace of this whole approach is that actually the prior doesn't matter so much if you have lots of data. But if you don't have lots of data, the prior can be really influential. What's the probability that Saddam Hussein in Iraq is building weapons of mass destruction? There was almost no data. We went with the prior. We were wrong. So estimation, we don't just have...
I'm sorry, I have a question. So if we apply Bayesian estimation of the SNP data set, we always got a lot of the SNP data sets. So if we do it with the Bayesian estimation, so like it's not that important to set what kind of prior that we use, right?
So it'll depend on how much data you have and how complicated your data set. And so what should be done in this case is you should investigate. What if I change the prior? How much of an input, how much of an influence would it have? But for a simple problem like estimating a proportion, the more data you have, the less the prior matters. The other thing that's different about estimation in a Bayesian framework is that what we get out of this, as I showed you with the red curve, is a posterior probability distribution, which has a maximum. So that's the estimate of maximum. You don't get the maximum likelihood estimate, we get the maximum probability estimate. And we don't get a 95% confidence interval, strictly speaking, because that is defined as in the frequentist sense. 95% of the time we go to the population and resample, calculate confidence interval, it will bracket the true parameter. In this case here, what we end up with is what's called a 95% credible interval. 95% of our belief falls between this value and this value, and that's our credible interval. So it uses the proportion of males as though it's a random variable and has a probability distribution. Even though in nature it's actually fixed, because we're uncertain about it, we model it as though it has a probability distribution based on how much information we have. So we're going to calculate one of these in workshop this week. Oh yeah, that reminds me. So workshop this week, we're going to use Bayesian methods to calculate how many elephants there are in this national park in Nigeria. And this is a data set that we already analyzed in the likelihood workshop. My recommendation before Thursday, do it again. Go back to the likelihood and just go through it because it'll make it a lot easier on Thursday. And if you haven't done it yet, do it twice. Once today, once tomorrow, and then come in on Thursday. So under frequentist statistics, we generate a 95% likelihood-based confidence interval. And that's what we would get. And the interpretation, well, it's sort of a folksy sort of interpretation. Most plausibly, P is between 0.19 and 0.62. But here's what it really means. A repeated random samples taken from the same population, likelihood-based confidence interval, so calculate with bracket the true population P, approximately 95% of the time. The 95% credible interval, 0.2 to 0.61, assuming case 1, non-informative prior. The Bayesian interpretation is that the probability is 0.95, but the population proportion lies between 0.0 and 0.61. This is a lot simpler to state, and it's one of Cohen's points, is that actually this is what we want. We want to be able to say the probability that the alternative hypothesis is true, the probability that the null hypothesis is true. And Is that true? Is that what we want to be able to say? I don't know. When I analyzed all the data, which was actually a much larger sample, 253 males, 489 females, the Bayesian estimate of proportion is the same regardless of the prior in these three cases. So that just illustrates what I said earlier, which is that the posterior has little effect. Okay, so how far are you willing to go with this approach? How useful is this? What can one do with it? Well, there's been a lot of arguments in the literature. You know, Cohen's essay that we read this week is not the first attempt to persuade us that null hypothesis significance testing makes no sense, and that Bayesian methods make much more sense. We understand better the outcome. We'd like to be able to say the probability is 0.95 that this parameter is between here and here. How would we do this if we decided to go Bayesian? How would you how would you do a two-sample t-test, or the equivalent of a two-sample t-test? Well, one thing that's been discussed in the literature recently is something called the Bayes factor. And it's been put forth as a Bayesian alternative to null hypothesis significance testing. And the idea behind the Bayesian approach is that it overcomes one of the most difficult parts of null hypothesis significance testing. So the conventional setup for a two-treatment experiment and the application of a two-sample t-test would be a null hypothesis. There's no difference between the means. And an alternative hypothesis, there is a difference between the means. But null hypothesis significance testing doesn't evaluate this hypothesis ever. It assumes this is true and uses that to calculate a p-value, and as a consequence we never ever have the opportunity to say, well, how much evidence is there for the null and how much evidence is there for the alternative? All we get is a p-value that tells us something about the null, and if p is small then we reject it in favor of the alternative. In my AIC lecture I gave you an example of a data set published by Mike Bell where he was unable to reject the null hypothesis of a random walk. But a reanalysis of that data that also specified what an alternative hypothesis might look like found far more support for the alternative than for the null. If you'll remember that example in my AIC lecture. So there are certain advantages to being able to compare the null with the alternative. The Bayes factor allows us to do this if we want to go there. If we apply the Bayes factor here, then we have the same null and alternative, but unlike null hypothesis significance testing, the null hypothesis has no precedence. It's not given a special weight, really. The Bayes factor is the ratio of posterior probabilities of the two hypotheses, the alternative over the null. And therefore it gives you an idea of how much more support there is for the alternative than for the null. But to do this, you have to have a prior probability for the null and the alternative hypothesis. And the way this is conventionally done is that, I don't know, before you collect the data, what's the probability that the null hypothesis is true? What's the probability that the alternative hypothesis is true? Well, if you take the no information, the flat prior, the I don't know explanation, then this is just one, and the prior disappears, and the Bayes factor is essentially the ratio of the likelihood of the alternative versus the null. And this likelihood is easy to calculate. That one's not, because we actually need a a probability distribution across all the possible values in the alternative hypothesis that might actually be the difference between the two means. Computer programs do that. But there's this kind of behind-the-scenes assumption that one does as to what the shape of that distribution is, but it's essentially flat. It just doesn't go all the way to minus infinity and plus infinity. Okay, so if the H0 and HA have the same prior probabilities, then the Bayes factor is just that. And then the remaining question is to decide, well, what constitutes strong evidence in favor of the alternative hypothesis? And the convention is to use a sort of a scale similar to the AIC scale that we talked about last lecture, which is that an AIC difference of this magnitude is considered some evidence but not strong, etc., etc. So here's sort of the conventional cutoff. A Bayes factor of 1 to 3 is basically saying there's only, there's the support for the alternative over the null is only 1 to 3 times. So most of us would say that's not particularly strong support for the alternative. It's supported, given the data, it's better supported than the null, but it's not huge. The Bayes factor of 3 to 10 is considered substantial. By the time you get to 10 or more support for the alternative versus the null, then you're starting to think, okay, now we're in the range of uncertainty diminishing. There's much more support for the alternative than for the null. So that's the way the Bayes factor approach works. And maybe the 0.95 equivalent would be, you'd want 20 times. You'd want Bayes factor to be 20 times before you accepted that there was strong evidence in favor of the alternative hypothesis. Okay, so convention is somewhere between 10 and 30. So does this work? And what kind of evidence does it give us that's different from what we already do, null hypothesis significance testing? So this was a paper, I don't have the author's name on here, Wetzel's et al. They went through the psychology literature and they obtained data, numbers on 855 t-tests that had been calculated, sort of sifting through the literature, and then reanalyzing all those data using Bayes factor. And so what's arranged in this graph is the p-value from the two-sample t-test, the conventional approach. What's arrayed along the y-axis is the degree of support for the alternative hypothesis using the Bayes factor. And when I first looked at this graph, I just thought, they're telling us the same thing. They're highly correlated.
What is that in that square where it's in this is 78%? What is that? What is that?
Oh, it's just cramming a lot of dots in here without trying not to have them overlap too much. Systematic jitter. So you could look at this and go, they're telling me the same thing, essentially. So what's the big deal? Here I have a method, we all know how to use it, it's simple, all stats packages are set up to do it. And now you're telling me that a Bayesian approach, which is promoted as an alternative, basically the result is highly correlated with what we would already get, which is true. So maybe that's a plus for the approach that we use conventionally. But then, a second look, we start to ask, well, here's our conventional p-value associated with null hypothesis significance testing. How much support for the alternative hypothesis does this actually represent? And the answer is hardly anything. So in a Bayes factor world, the equivalent of p equals 0.05 is anecdotal evidence for the alternative hypothesis. So under this framework, p equals 0.05 is very weak evidence that the alternative hypothesis is true. And it's not till we start talking about 0.001 that we're getting up into the range of strong evidence for the alternative hypothesis. So the upshot of a lot of these discussions is now, okay. We're not going to convince the world to go Bayesian. What we'll try and do instead is convince everyone to use a different threshold, significance threshold. And so there are papers like this one, Revised Standards for Statistical Evidence, where a lower p-value is what, we should either use Bayes factors, or if you're not going to use Bayes factors, you're going to stick with null hypothesis significance testing. Use 0.001 or 0.005 as your cutoff, because otherwise the evidence is just too weak. There's a Bayesian model selection analog to AIC. The resulting formula looks a little bit different. I'm not going to go into it. It's derived from a completely different theory. It actually gives you, posterior probabilities under certain interpretations. And you'll hear about this again. People have been arguing for a long time that we should be using Bayesian methods. Bayesian method is just philosophically much more pure, and so on and so on. It gives us what we really want. We want to be able to say probability of the null hypothesis is false or true, and p-values don't allow us to do that. But for the longest time, there haven't been actually any methods, because the methods are actually pretty complicated to replace, like even the calculated Bayes factor. You can't do it by hand, whereas you do two-sample t-test by hand. And it's only really in the last decade that tools have started to become available that you can actually do Bayesian analysis of biological data. And there was a package called WinBugs, and now STAN is all the rage. You've perhaps heard about STAN. He's all the rage. Lizzie Wolkovich is a prophet of STAN, and she gave a workshop here this past summer. And she'd be happy to tell you more about why you should all be using STAN. But it's a model fitting platform that allows you to incorporate priors in calculating. The calculating fits of models to data. And all these packages have R interfaces, so they become easy to use once they interface with R. So to summarize, Bayesian probability is completely different. A completely different definition. But we can use it to estimate and test hypotheses using the word probability, because it's a metric of our uncertainty, but in this case it's degree of belief. It requires prior probability. The influence of the prior, however, declines with more data. The interpretation of the interval estimates is completely different. If the Bayes factor is a regional approach, having the advantage of telling you not just whether the null is true or false, but how much support is there for the alternative compared to the null, then we need to revise our standards of evidence that we currently use. And like it or not, Bayesian ideas are being used much more in ecology and evolution. I just wanted to point out. Yep, another paper, again, arguing for, this is in Nature, human behavior. Another paper with many important names, again, asking for a different p-value threshold, and they suggest that it should be 0.005, so we should revise it an entire order of magnitude. Actually, this did not go over well with all readers.
Oh, no.
That's my introduction to Bayesian ideas and how they might be used without any of the details. We'll get a chance to actually apply some of this technology in our workshop on Thursday. So, and the first case is the elephant population size. The discussion paper for next week is online. I've got a couple of presenters. Need a couple of moderators. So So if you want to moderate this discussion next week, come up and see me, otherwise R will choose. Any questions? Okay, see you Thursday.